Good afternoon. I hope everyone is having a good day wherever you are. We are going to talk here about learning curves, and more precisely how we can be confident in the learning curves we obtain in additive factors modeling. I am Cyril Goutte, and this is joint work with Guillaume Durand at the National Research Council Canada. What are learning curves? Learning curves, or performance curves, plot the error rate or the performance of students on some test items as the opportunities to practice grow. They are an important tool when we are trying to diagnose how students are learning. Typically, as students practice a skill and the number of opportunities to practice that skill grows, we expect that the error rate will fall, indicating that students are actually acquiring the skill and getting better at using it. There are actually many types of learning curves. The plot on the right shows an empirical learning curve in red. It records the observed rate of errors made by students at each opportunity to practice. Because it records the empirical error rate, the red curve goes up and down a lot. This is due to the fact that we average over a limited number of students at each opportunity. Also, students have different levels of proficiency. There is also the impact of attrition, as students who master a skill tend to move on to other activities, leaving only less proficient students at higher opportunities. The blue curve, on the other hand, is an idealized learning curve for a student of average proficiency obtained from an additive factors model estimated on this dataset. Because the blue curve is mediated by a model, it is much smoother than the empirical curve. It actually shows slow but steady learning as shown by a reduction in error. Several other types of learning curves have been proposed, for example, to compensate for attrition or take into account average learning over a population of several skills. Our work is taking place in the context of the Additive Factors Model, or AFM, proposed by Sen and colleagues back in 2006 and used, for example, in the PSLC data shop. AFM models the probability of success of a student on an item as an additive combination of several elements: the proficiency of the student, the easiness of the skill, beta, and the learning rate, gamma, which models how quickly performance improves with additional practice. The mapping of skills onto test items is provided by the use of the Q matrix. The probability of success grows with opportunities T through a sigmoid function, shown here on the right, transforming the linear combination of parameters and opportunity into a probability. This model produces well-behaved, non-increasing learning curves for all skills in the competency model. The additive factors model is estimated from empirical data collected from observing interactions between students and test items, given a competency model expressed in the Q matrix. This is typically done using something like a penalized maximum likelihood method to obtain the best AFM parameters for this set of observations. These parameters yield the best model for that combination of dataset and competency model. From that model, we can produce various outputs to diagnose learning, for example, learning curves mediated by the model showing how well a particular skill is acquired. Note, however, that parameters are estimated from a finite number of specific observations. A different set of observations may lead to different best AFM model parameters, and a different competency model mapping items to skills definitely will. This means that there is some intrinsic uncertainty associated with the model parameters. This is captured by the covariance on estimated parameters. As AFM is a statistical model estimated from data using a kind of maximum likelihood method, statistics tell us that under mild regularity assumptions, the estimated parameters are asymptotically normally distributed around the true parameters, with a covariance given by the inverse of the Fisher information matrix for the model. Given the model, we can compute the Fisher information matrix at the estimated parameters and derive the covariance between those parameters. We display on the right the covariance between the easiness beta and learning rate gamma for a specific knowledge component, number 11, in a model obtained from the geometry dataset in the PSLC Datashop. We see that the confidence interval characterizing the spread for each parameter is quite large. It would go from around minus 4.5 to around minus 1.5 for the easiness beta, and from around 0.6 to 1.8 on the learning rate gamma. This is a factor of 3, which is huge. However, we also see that beta and gamma are very correlated, and we will see in the following how this allows us to derive much tighter error bars on the learning curves. This is the straight learning curve for knowledge component number 11 in this model of the geometry area dataset. On the left, we see again the distribution of parameters obtained on the geometry area dataset with the optimal beta and gamma parameters indicated as a red dot in the middle. Using these values of easiness and learning rate, we compute the idealized learning curve for a student of average proficiency, shown on the right for knowledge component number 11. In this case, it shows that according to the AFM model estimated on this data, knowledge component number 11 is challenging in the beginning, but relatively quick to learn. After only a handful of practice, the error rate is minimal for the average student. But how confident can we be in that result? Is that typical, or can it be a fluke of that specific data estimation? One way to answer that is to look at the uncertainty on the actual parameters and derive, for example, the learning curves corresponding to the extremes of the confidence intervals. On the left, we still have the optimal AFM parameters as a red dot, but we added the confidence intervals on the easiness beta and learning rate gamma as blue lines. Taking the extreme values of the confidence intervals for both parameters allows us to derive an upper confidence learning curve and a lower confidence learning curve shown in blue on the right. The previous learning curve in red tells us that by opportunity number 3, the error rate should be down to about 30% on that scale. But error bars now suggest it could be as low as a few percent or as high as 95%. Are we confident that anything in that scale was learned? Clearly, the extremes of the confidence intervals actually correspond to extremely atypical values. Let us now see how we can exploit the distribution to get a much more realistic estimate of the confidence on the learning curve. In order to get a better picture of the uncertainty on the learning curve, let us sample parameters according to the distribution of beta and gamma and see what learning curves these would correspond to. In this example, the sample set of parameters shown as a dark cross on the left produces the learning curves in black dots on the right. It is clearly different from the red curve resulting from the estimated model, but it is not as different as the blue curves showing the marginal error bars would suggest. We sample 2 more sets of parameters and produce 2 more learning curves that differ from the estimated one in more or less subtle ways. We continue sampling parameters to produce more learning curves, and we start to see a realistic spread around the estimated learning curve, representing the typical spread of error rate around that curve. Once we have sampled enough parameters, in this case 200, we can now use, for example, quantiles on the sampled learning curves in order to get much more realistic and tighter error bars on our model learning curve. At 4 opportunities, the resulting 90% error bars on the learning curve, shown in red here, goes from about 5% to around 28%, versus 0% to 90% for the marginal error bars given by the blue lines. This is a reduction of a factor of 4 to 5 on the uncertainty, indicating a much better confidence on the estimated error rate at 4 opportunities, which according to the AFM model is 12%. In our paper, you can see examples of how this can be used to systematically diagnose all skills in a competency model, or to compare how similar skills are modeled in different competency models for the same data. This can be done on the basis of the learning curves, but also and especially on the basis of the confidence on those learning curves. In conclusion, we have been talking about learning curves, a crucial tool for assessing whether students are actually learning and how. Because EDM models, such as the Additive Factors Model, are estimated on finite amount of specific data, there is some uncertainty on the model parameters and resulting learning curves, which we must be aware of. Quantifying uncertainty through the use of error bars or confidence intervals is essential to be confident in the conclusions we are drawing from our models. We have seen that looking only at the uncertainty on individual parameters grossly overestimates the size of the error bars, making it hard to draw confident conclusions. We showed how a sampling approach allows us to get a much better quantification of uncertainty, much tighter confidence bounds, and therefore reach a more confident diagnostic of learning. Finally, we illustrated how this works on idealized learning curves, but this can be applied straightforward on any type of learning curve that can be derived from the model parameters, including the completed or the averaged learning curves. Thank you for listening, and I will be happy to answer questions here or by email.